Again, so if you guys are looking for a place to start here, make a little 3-column table. And like I said, the hope is that eventually you start to see some patterns and be able to be a little more efficient instead of just plotting it laboriously. But if you got to do it, you got to do it. I'd say that these slope fields are a little bit larger than what I would typically expect you to do. The time constraint of a quiz or a test. It's good practice for class though. We'd take a few minutes here. I thought I'd go through this a little bit slower because this is probably the toughest of the group. And we'll plot some of these points out. We'll start to look for some patterns here as well. Maybe I started off with 1, 1. Maybe I should also do 0, 1. If I do 0, 1, dy dx is 1. And so that would be right about there, give or take. And I don't know, maybe I try 1, 2. If I try 1, 2, the slope is 3. And this is where I start to see a pattern emerging. Check this out. I think to myself, all right, 1, 2, the slope is going to be 3, so that's steeper. And the next thing I arrive at is, you know what, as I move on that line, as I move to the right, they're just going to get steeper and steeper, right? And so I would say I don't even really have to figure out a numerical value for this. I mean, it's not that hard, it's 4. But I'm just going to try to make sure that that is a little steeper than the one just to its left. That make sense? I'm starting to see patterns. And then I start to think, well, I wonder if that steepening pattern is true for the row above. So I start off with 2, 0. Or sorry, 0, 2. So 0, 2, dy dx would be 2. So that's about like that. And maybe I try 1, 2. And as soon as what am I doing? Sorry, this was, before should have been 2, 1. I did eat lunch, but it seems like I didn't. There we go. So I try 1, 2, and I get 3. And I start to see that same pattern emerge, right? The further I go to the right on that row, the steeper things are going to get. So this gets pretty tough after a while to get these to be as steep as they need to be without going beyond vertical, right? So you can see kind of that pattern of the further to the right you go, it seems like they get steeper and steeper. Does that make sense? Maybe we try it on the x-axis itself. 0, 0. The slope is, or dy dx is 0. And I try 1, 0. It's 1. And then I start to see a pattern emerge. I remember that this is a 1 slope, right? And I start to ask myself, I wonder if all of the slopes on that diagonal are 1s. Like dy dx being 1 there. And I think you'd find out pretty quickly that that's true. So this would be an opportunity to use a pattern. So I would just go dy dx is 1, dy dx is 1, and dy dx is 1. The way you could do a little bit faster. I'm starting to see a pattern emerge. Okay, and then I'm going to use that steepening pattern to the right, and then I get to about there. Making sense? I don't know. Maybe you're curious about. Maybe I'll do this one over here. I guess it would be 3, negative 1. That would be a dy dx of 2. So maybe something like that. Maybe you're curious about that 0 slope and start to ask yourself, I wonder if there's a pattern for all the 0 slopes. Isn't the truth that all along this diagonal pattern, the x and the y coordinates are opposites? And if you add opposites, what do you get? 0. All right, so that's kind of a handy thing to notice. So then these would all be dy dx being 0. And I get this. Making sense? And then I start to realize that there's a lot of diagonal patterns going on with this, right? So same, 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 same. Same. So it appears that everything is on a diagonal, like on a 45-degree angled diagonal. All those dy dx's are the same numeric value. So then I wonder if I could just use that, and maybe I try this negative 1, 0. I get a slope of negative 1, and I would pretty quickly realize that my pattern is pretty good because I'd get all these. Once you start to notice the pattern of, well, on all of those, the x-coordinate's a negative number whose absolute value is 1 bigger than the y value, you're going to get a negative 1 for dy dx all along those. And then perhaps we have a the same pattern developing. Maybe this point right here would just be a steeper negative. I think we could confirm that negative 3, 1 has a dy dx of negative 2, and then we would get this negative 2 slope. Then we go with our diagonal pattern. You see how this can be quicker than first appears? Once you start to see patterns, use them. And if you look at it and you're like, whoa, that pattern doesn't make any sense, you know what you do? You just plot it real quick and say, okay, yep, negative 3 plus 1, in fact, is not 2. It's negative 2. And you fix whatever little error you made. It happens to everybody. This would be a little bit steeper negative. This would be that same slope on the diagonal pattern. This would be even steeper. How about that? And that. And this would almost look like it's vertical, something like that. Okay, and you end up with some lovely graph like that. I saw a lot of those. You guys have any questions about any of those points, the process I used, or pattern finding? Pattern finding is a really awesome skill to work on. That's math. A lot of the time it's just about finding patterns and stuff. So kind of a good practice for doing that. Anything at all? Okay, well, let me ask you guys a follow-up question. What if I told you that the solution to this differential equation had an initial condition of that? Y of 0 equals 0. What do you think the solution curve would look like? If y of 0 equaled 0. Draw it out, or do your best. The solution curve would actually be the graph of that original function, right, reduced to this derivative. Be the function that somebody differentiated to get this. Well, this is a pretty curvy graph, right? Depending on which part you're looking at, sure. Y of 0 equals 0. So the slope fields are just kind of the pattern for the graph. So, does this make sense?
Yeah, that makes sense.
Kind of like following those little... We haven't talked about the left side. Yeah, we haven't talked about the left side yet, right? Does that make sense? There's a little bit of a glitch in mine there. You can see it should be a nice smooth curve, but that part makes sense. What do you guys see? Like when you see that little slanty diagonal line that appears right in the middle?
Like this.
Yeah, doesn't that look like an asymptote? Like the other day we had that horizontal asymptote we looked at. Maybe this would be one of those slant or diagonal asymptotes. What do you mean a jump to a linear? Well, let's look. I think it would look something like this in the end. It's gonna curve toward this, and long term, like when you think about what a horizontal or a slanted asymptote mean, they're talking about long-term behavior, right? As x gets really closer and closer towards negative infinity, or in other cases, as x gets really close or closer to positive infinity, we're talking about that long-term behavior. I gotta say, I have to think about this. I'm pretty sure this is the exact slope curve. It's hard to say. I don't know if it does that or if possibly it does that. I would guess that it probably does the first thing that I said. We could confirm that for sure if we wanted to, but first glance, I'm not for sure. Does that make sense for a solution curve? Let's do another one. What if we had a different initial condition? What if it was y of negative 2 equals, I'll go y of negative 2 equals 0. We'll just do that. What do you think that solution curve would look like? Keep in mind these are two totally different solution curves, right? Remember, a solution curve has to be a function. And if I included both of these, I think we'd run into it not being a function. That's the whole vertical line pattern.
It just follows that line.
I think you're right there. I want you to see my Snapchat story.
That's hard to decipher, right? It's got to go through 0, 0.
That's right.
Thank you.
You know, for the Sounders, they were going to have our backup goalie do it. Jace Root.
Oh, yeah. They should have had Jace. Yeah, Jace would have been amazing.
He would have been so good.
And I honestly, without actually solving this, I wouldn't know. I mean, could the RPA should have gone to the right of that upper slope field?
Jace could make anything fun.
Jace would have been amazing. I forgot he was just a sophomore. I thought he was a junior.
He can make anything. Yeah, he's
A lot more complicated than that, actually. Yeah.
a
This is an interesting one, yeah.
The most confusing part was
Okay, let's see here. Negative 2 comma 0 is right there.
oh.
Right?
What do you mean?
Sometimes I mix those up too. All right, so does this one appear to be doing that? You think? Like kind of approaching that the slanted asymptote from below? But then as you kind of follow the slope fields, doesn't it appear to kind of like dive off the bottom of the graph?
Yeah.
Like the lower the y values, the more negatively steeper it gets. So I would say this thing is just going to drop completely off the bottom of the graph and just get steeper and steeper and steeper the lower the y values are. And then it would approach that slanted asymptote. Hey, let me ask you guys kind of a backwards question. Listen up, please. This might be super easy. This might be hard. I'm not for sure how this is going to go for you. So you got the red and the green solution curves up there. If I wanted that slanted asymptote to be my solution curve, what initial condition, or what would be one of the initial conditions that I'd need to have? Y equals, you said y of negative 1 equals what? 0? So let's see here. Negative 1, 0 is right there. Do you see how that's right on the point that generated that linear pattern? So I think I would agree. So that one right there, I'll try to be precise about this. So this purple line would be the solution curve for what Julia mentioned. And there would be others, right? You could have 0, negative 1. Or you could have negative 2, positive 1, amongst others. Okay, how are we doing? So this one is a little... This one is significantly harder to solve as far as solving the differential equation. In fact, if we were going to try to solve this differential equation, we'd have to admit that it's beyond the scope of our class. Because if I were to come over here and say, let's figure out what this graph would be, and I would try to separate the variables, right? You could get yourself into all kinds of trouble here, assuming that you could separate the variables. You would find out pretty quickly that you cannot separate these variables using the typical way, like multiplying dx over or something, or maybe you subtract the y over, but if you do, you're still going to get x's and y's together. This is what's called, and this is beyond our course, this is called a first-order linear differential equation. So this would be a Calc 2 topic, although it's not even in Calc BC, but if you took like maybe a college calculus 1 or 2 course, you might get that in there. If any of you are super duper interested in seeing it, I'd be happy to go through it with you. But here's just a real quick demonstration. So you'd have to do a little rearranging, and you have to recognize that the number attached to the y is -1. Right? It's -1x. And you have to get this thing called an integrating factor. The integrating factor is e to the integral of whatever that number was, dx. So that would be e to the -x. Then you'd multiply everything through by e to the -x. And after all was said and done, you'd find out that you're just reversing a product rule. And then you'd proceed. So, like I said, I'm not interested in like trying to teach you how to do that because I feel like it could be some confusion. Then you'd start seeing first-order linear differential equations everywhere, and beyond this, you really won't see them much, if at all. Fair enough? But there is a way to do it. So this is going to be it as far as here in class, us drawing slope fields and probably drawing solution curves, at least for the moment. So do you guys have any last questions before we leave this alone? Okay, so let's talk about some of the other things we might do with this. So if you guys could flip ahead. Sometimes you might be asked to draw a slope field, just like we've been doing. Other times, you might be asked to do a little matching game. So if you guys would, please try number 7 through 10. 7 through 10. Matching the differential equation with the slope field. Just consider what you might do to figure out what goes with what. You guys thought number 7, dy dx equals sine of x. What did you guys think about which one that was, A, B, C, or D? C? Okay, anybody want to explain why you thought C went with number 7? What did you see, Robbie? Okay, so yeah, some periodic motion, and that seems to go with sine. Like none of the other ones have that, for sure. I agree. I think that's reasonable for this one. How about number 8, dy dx equals x minus y? What do you think that would go with? D? Anybody want to offer up some reasoning as to why you chose D? It kind of looks like the last one, but it's instead of x plus y, it's x minus y. What if, let me ask you this. What if maybe there was other more complicated options, or you were kind of thinking that, but you're like, oh man, every time I think it's going to be easy, it's actually really difficult. So I better like check to make sure that really is the thing I think it is. What could you do to confirm that 8 really is D? What do you think? Put in a few points. That's going to be a great strategy with these. So, maybe, you don't know exactly where the points are, but maybe you identify this whole, you get this pattern right here where it appears that dy dx is 0 because of the horizontal nature of the pattern there. Yeah, so maybe you look at that and say, well, does that make sense? Well, look at there. Let's plot some points like Jake suggested. 0, 0 has a slope of, or has a dy dx of 0. 1, 1, 1 minus 1, 0. You do enough of these, right there, that'd be -2 minus -2. You'd confirm, okay, this in fact does look like 8 goes with D. So once we do number 9, we'll have a good sense of number 10. What do you guys think number 9 is? 9 is A? Okay. Anybody want to offer a reason as to why you thought 9 was A?
Isn't it when you're only dealing with a y, you're going to have a horizontal pattern?
You guys listening? That's really, based on the set of options you have, that's probably the best, most efficient reasoning. You can see a horizontal pattern that goes with when, like she said, dy dx, it depends only on y. I think that's very reasonable. So then we finally end up at number 10 would have to be a B, right? Now, does that actually make sense? Why? Yeah, you see the vertical pattern on the slope field, and dy dx only depends on x. That actually does go together. And if any doubt arises, just do what Jake said. Plot some points. See if it makes sense. If it doesn't make sense, either your arithmetic's bad or you messed up. Go back and try to fix it. All right, so there's that. So I wanted to point out that this was taking slope fields and trying to match them with differential equations. I think at some point in here you're going to notice a slightly different task. But let's do this next. If you haven't already looked at numbers 11 through 14, please do. This would be maybe slightly harder. But we'll do that, the one I was referring to, we'll do that here in a second, and you might find that to be a little more challenging. A, B, C, D, 11 through 14. So Julia was really vocal a few minutes ago. Tim said a little bit. Dax maybe said something. That was basically it. So the folks that were a little more vocal last time, let's give everybody else the chance to speak. So what do you think? Number 11. What do you think number 11 goes with?
B.
Say again? B. Okay, so 11B. Anybody want to offer a suggestion? Several of you said B. Why do you think B actually goes with 11? What's your reasoning? Vertical pattern. And none of the other options, 12, 13, 14, none of them have dy dx depending only on x, right? So I think that's pretty reasonable. I think you could plot a couple points as was suggested and see it really is true. Okay, number 12 goes with C. Okay, so 12 goes with C. Anyone, again, let's offer some reasoning why you think 12 would go with C. Horizontal pattern, dy dx depends only on y. Oh, man. Check out the awesome C and D, or C and B. Okay, so now we're down to 13 and 14. And you can, of course, see that neither a horizontal nor vertical pattern exists on either of those. So what did you guys think for 13? D. Okay. So that leaves E for 14. Can I try to get in? A, sorry. I'm just going in alphabetical order there. There we go. A. You're like, E, where was that? This makes no sense. So here's what I'm guessing. You probably looked at 14 and you recognized that A was the same slope field we just built from 5 minutes ago, and you thought, oh, of course those go together. But let's try to picture this. What if you hadn't done that? What could you do to differentiate between 13 and 14 and D and A? Yeah, you got to plug and chug, and I think there's going to be some points that are helpful, others that aren't. I'm looking at this, and I see up here and up here, I see slopes of 0. So that tells me that whenever the x-coordinate is 0, dy dx is 0, and to me that only works with this one. So you can pick out some key, like distinctive points and try to match those up with your differential equation and slope field. And you should really, honestly, given enough time, be able to confirm all of these, right? There's always going to be some time element in a quiz or a test, but given enough time, you plot a few points, you should be able to get to that spot where you're like, okay, finally figured it out. That's it, right? Okay, so then, are there any questions about those, the two matching sets? That's great. All right, so then the last one we're going to do here on these slope fields, please don't cry, this will be the last slope field to do together here in class, is number 15 right here. This is a little different because in the two previous matching sections, you were given slope fields and differential equations. Please notice here, you're given a slope field again, but you're given solution curves, not differential equations. So I can think of two pretty distinctive ways, at least, maybe you could think of a third or a fourth. I can think of two distinctive ways that you could figure this one out, like reasoning-wise. So take a few minutes without a calculator and see if you can figure out what goes where and which one matches with that slope field. Okay? Ready to go. Okay, so it's not A. What do you think? Is it B? You arrive at B, y equals e to the x for a solution curve for that. Nobody goes with B. Okay, so it's down to C, D, and E. What do you think? Is it C? C. I got a halfway hand raised, maybe half a vote for C.
I forget what E.
Okay. How about D? What do you think? D, cosine, y equals cosine of that? So do, 16 and a half of us think that it's E? So everybody in here, maybe most of us think it's E. Okay, let's find out. So let me show you. It's going to be one of those situations where either most of you are happy or most of you are like, what? I thought it was E. Okay, so here we go. Here is the way, here's the way that you could do this a little more of a process-oriented way. To me, it's easier to match up a differential equation with a slope field because they're directly related as far as actually getting the numerical values to put onto the slope field. So here's what you could do. You could look at this and say dy dx equals 2x and dy dx equals e to the x. I saw some of you doing this. I thought this was a good strategy for sure. This equals negative e to the negative x. Over here, it's dy dx is equal to negative sine of x. This is dy dx is equal to 1 over x. So from a process perspective, you just whip those derivatives out real quick, and we start comparing and plotting points. We have some scaling here, like it's 0 to 3, so there's maybe 1, there's 2, 1 and 2, something like that. So you can start plotting some points. So I'm kind of a fan of the point 1, 1. I think that'll help. So if I plot the point 1, 1, and by the way, these all depend on x, right? So it's really only about the x's. So if I plot the point x equals 1, for my first one, my slope is, does that look reasonable? It does. So I don't think we've eliminated a at all. B, this would be e to the first if I plugged in a 1. Does that look reasonable? Because e is about 2.7. Does it look like those slopes could be 2.7-ish? Maybe. I mean, we're on the fence there. That's a maybe. How about C? If I plug in x equals 1, isn't that one immediately eliminated? Because that would generate a slope of negative 1 over e. The important thing being negative, right? Clearly, positive dy dx is there. So C is out. C is out. Okay, dy dx is equal to negative sine of x. So sine of 1, we can actually sort of do this. Sine of 1, that would be in the first quadrant, wouldn't it? And in the first quadrant, sine is positive. But then the negative of that would be negative. So that's out, right? Because we can clearly see the slopes are positive when x equals 1. And then e, still in the running, because when x is 1, dy dx is 1 over 1. That also looks reasonable, doesn't it? Okay, so let's try x equals 2. If I try x equals 2, the slope for that for a would be 4, wouldn't it? And here's where we get to eliminate a from the mix, because if the slope right here at 1 was 2, the slope at 2 would be 4. Shouldn't we see these being steeper than those? And we don't see that. Right? dy dx equals 2x. The bigger x gets, wouldn't it get steeper and steeper and steeper? And we don't see that pattern at all. So based on the pattern, that's out. So at this point, we're down to just b and e. So let's try the 2 again. What would be the slope of the solution curve if b was it? If we were looking at the solution curve slope at 2, the slope would be e to the, and close to 9, right, like you said. So here at 1, if b is it, the slope would be e to the first, so it would be just like a little bit less than 3. And then 2, the slope would be almost 9, right, between 8 and 9 maybe, something like that. We can see that that's not the pattern at all. We should see a steepening pattern if that's the case. And don't you see a getting less steep pattern? So I'd say based on that, we could eliminate b, and it would seem like e is the right answer. And it is. It is the right answer. So that's a very, labor-intensive process. Find the derivatives, methodically plot some points, look at patterns, decide does this make sense, yes or no. It requires some knowledge of, just kind of what E is roughly. Like if you had no idea that E was about 2.7, could get you in trouble if you're just like, I have no idea what E is. You probably ought to know that E is just a little bit less than 3. I think that would be a handy, fun fact to know. You want to know the fast way? If you know parent graphs, this is over in 10 seconds. So check this out. Maybe this would be an encouragement to you to go back and review parent graphs. First one's easy. Here is x squared. Does that match the pattern of slope fields? Not at all. A is out. e to the x. Looks pretty similar. It's an increasing exponential. Does that look like the slope fields? Nope, it's going the wrong way, so that's not it. E to the negative x, I'll start over here, has negative slopes the whole time. That's not it. Cosine of x, you probably figured this one out pretty fast, right? Cosine of x would go, well, it doesn't quite go through there. It'd be something like that, right? It's like not even the same zip code, is it? Right? I mean, it's totally different. Doesn't make any sense. And then finally, if you knew ln really well, doesn't ln look like this? Mine's not perfect, of course. I'll try again. That actually looks pretty good, doesn't it? If you knew your ln parent graph, you'd look at this and be like, oh my gosh, I know exactly what that parent graph looks like. And whoa, look at that. We get these. Oh, it's perfect. It's ln. Done. Right? And so a knowledge of parent graphs would be super helpful here. Not mandatory by any stretch, but would be super helpful. Okay. Did anybody think of a third way? Those are the only two ways that I came up with as far as how you could do this one. I don't know. Anybody else have a different thought? All right. Fair enough. So at this stage, we're done with slope fields, and I want to point out a couple things about this. If you notice, if you keep going, there's another matching exercise, 16. 17 has 5 parts. 18 also has 5 parts. 17 and 18 are a little bit past you right now as far as everything we've talked about. And so what I would want you to do with numbers 16, 17, and 18 is to think of those as like extra practice problems. So in a couple of weeks when you're looking to study for your quest over this material, that would be 3 additional sets of questions that you could use to, and there's answers on the end too. You could use those to kind of help you practice a little bit. Yeah.
So the quest is next Friday. That's like the one that's in school. The test.
No. So next Friday is the chapter 5 test, and that's over the stuff that we've already finished.
That's next Friday.
That's next Friday, and then the quest on this, and the quest is one of those ones that could go either way, and we'll talk about that. Of course, we already have a little bit, but that's got to be at least a week past that, maybe week and a half, something like that, I guess. Yeah. Maybe 2 weeks. Yeah. Okay. Any other questions on any of that? Okay. So then the final thing would be this. There's all the answers. So then for you guys, it would be Tuesday. There is an intro video, and it's on differential equations and exponential growth and decay. So this is kind of an exciting thing for me because in Algebra 2 and pre-calculus, did you guys learn about like I equals PE to the RT? If you learned about exponential growth and decay, maybe it's bacteria, maybe it's radioactive decay. I don't know. There's lots of different growth and decay models that we use. You're actually going to find out where those come from, when they're realistic, when they're unrealistic, and maybe an alternative to those as well. So make sure you watch the intro video before Tuesday's class, and we should be good. Okay? So I need Addie and Kayvon to skedaddle.